Yeah, today we're doing electrochemistry today. Yep. So yeah, at this time of year, it stinks because this is the time of year when it's prettiest outside and I want to be outside and enjoy the beautiful weather, but it makes me sound like this if I do. And I'm still paying for it. And I have taken like as many drugs as I can take and still be functional in here. So I can't, a lot of them make me really sleepy and stuff. And so I don't want to be like sleepy while I'm teaching. So I had to go light on the drugs. It was just so pretty. Yeah, it's right there. You just gotta press down and do it like you mean it.
Hello?
Yeah, let me see.
Yeah, I think it's full. Oh yeah, it worked. Will it automatically stop once it's too sharp?
Ooh, well, sometimes. There you go.
Thanks.
Yep. I got to see my best friend this weekend. That was awesome. Because she doesn't live here, so she lives in Virginia. Yep, her daughter plays softball for Meredith College. Meredith College. It's a women's college in Raleigh, North Carolina. And her daughter plays softball for Meredith, and they had
Lots of men, women, men.
yeah, there's more women's colleges than there are men's colleges, but there are some. But she had a tournament in Florida and then in LaGrange. So yeah, so my best friend and her husband and her son and her dad and her brother all went to Florida. And then everybody except my best friend and her husband left. And then they went to LaGrange to watch my best friend's daughter play. And then I was going to go down and she's like, they haven't even put her in for the last 4 games. I don't want you to drive an hour and a half to LaGrange and they not put her in. And no sooner did she say that than they put her in. So I didn't get to see her play, which is what I was going to do. But then after that, they just drove up here and my best friend and her husband spent Sunday night, which was nice because I don't get to see her much. So it was cool.
Virginia to go to West
Yeah, you would from here. Mm-hmm. What'd you do in West Virginia? Skiing or something?
No, I went to the Atlantic Ocean.
Well, that's in Virginia. West
Virginia.
Yeah, West Virginia doesn't touch the ocean. Virginia does. If you went to the ocean in Virginia, then you were probably in Virginia Beach, where I'm from. Yeah. Tis a lovely place. A lovely, lovely place. All right, so everybody should have gotten their Q3 progress reports, right?
Yes.
Yes, good deal. Everybody's doing pretty well. I still had some people who were surprised by assignments that they didn't turn in. They got zeros for. I don't know why anybody's surprised. It should be pretty obvious. So there's that, and then
Get a 0 on every assignment. When I do a lot of assignments.
Yeah. And then this unit that we're in right now that we started last week, the reaction rate in electrochemistry, it's very short. It's only last week and this week. After today, you have another test, and then we're going into our final, kind of our final unit. The final project is a unit in and of itself, but the only unit that I'm teaching after this electrochemistry one is the one on nuclear and organic, which is perfect because does anybody know what organic chemistry is?
Organic chemistry is what is so not we're studying non-organic.
Well, we're doing electrochemistry right now, but we're going to do nuclear and then organic. So organic chemistry is chemistry that deals with carbon-based structures, and it's all things living. It's the chemistry of living things. So it's it's the perfect bridge to go into biology for next year. So we start with a good organic chemistry understanding before we kick off biology, which is great. It's a good way to do it. So today is our last bit of the electrochemistry, and today in lab, you're going to be separating water into hydrogen and oxygen. And it's so easy that you could even go home and do it again if you wanted. You could do it in your own house. So it's not that hard to do. It's really kind of fun. All right, so we are going to talk about galvanic cells and electrolytic cells today. And pardon me if I have to stop and every so often. So I want to start with a historical perspective, and some of you are familiar with this story and some of you might not be, but this is a really fun story. And it's one of the stories that I hope when you leave this class, I hope you remember it because it's so super interesting. Okay. So a historical perspective about electrochemistry in general. So first off, we go way, way back to 640 to 546 BC, and we had this dude, Thales of Miletus. And he's credited with the discovery that amber, when rubbed with a cloth or fur, acquired the property of attracting light objects. Do you know what amber is? Amber is a semi-precious stone, but really what it is it's like petrified tree sap. It's like tree sap that's been turned into a stone, right? And people wear it like jewelry. It's kind of an orangey, kind of this color, amber. And sometimes you can find insects trapped in it. And if you've seen Jurassic Park, they found like a mosquito or something trapped in amber, and they pulled the DNA out of the mosquito because it sucked the blood from some dinosaur, and that's how they got dinosaur DNA to begin with. So amber can have preserved living things in it. But what he noticed is if you rub it with a cloth or a fur, it can suddenly attract objects that don't have a lot of mass. What kind of electricity does that sound like to you? It's electricity, but it sounds like something you're probably really familiar with. Light objects, not lighted, light, like not a lot of mass.
And like pull it to
Yeah, what does that? Does it sound
magnetic.
like static to you?
Oh,
Oh, yeah. And your hair sticks to it?
Yeah.
Yes, that's the same thing. So he was taking cloth or fur and rubbing it on this stone very rapidly like this, and then noticing that small things like bits of dust or whatever would stick to the stone, right? So he's basically, it's static electricity that he's playing with. Yeah, I mean, it could, yeah. Amber's usually, a lot of the time you can find, well, we polish it. Sometimes it can be very smooth. So that's probably why it worked better than some other rocks. But you know, like if you do that, if you rub a balloon on your head or whatever, right? So the word electricity comes from electron, spelled a little differently than how we spell it, right? And that's a Greek word for amber. So now we know where electron came from. It came from amber, because that's where somebody first noted static electricity. So he named it for the stone. So that's really interesting. That's where we get electron from, amber. So then move forward many years later. Okay. Now we're in the 1600s, and there's this guy, Otto von Guericke, and he invented the first electrostatic generator in 1675. And it was made of a sulfur ball, which rotated in a wooden cradle. The ball itself was rubbed by hand, and the charged sulfur ball had to be transported to the place where the electric experiment was being carried out. So he would carry this big sulfur ball. It must have been fun because sulfur smells terrible. Basically, he's spinning it in this cradle, right? And when you spin something, you can create static electricity. So he's creating static electricity with a generator that he has built. Yeah, same kind of thing. Or you walk on the carpet and then you touch the doorknob, zap, right? So he was probably seeing, like, if it's dark enough and you do that in a dark room, you can actually see the little spark. So he was probably seeing some little sparks, maybe even little arcs between his little sulfur ball and his spinning thing here. And it was probably making that crackling, popping sound, which is very exciting. Everly, you can shift over if you can't see. I know the light's right in your face. All right. So then eventually a glass globe replaced the sulfur sphere used by Guericke. So it looked more like this thing here. So this is a reproduction of a static electricity generator from the 1600s. And then later we get these discs. Okay, so we had this guy with the glass globe, and then we get these big, large discs. All right, so now we have discs that we're using when we're generating static electricity. You can't do much with static electricity. You can't run like a circuit off of it, right? It's not a current that flows.
You need the activation.
Yeah, you need something to keep it flowing, and it's not gonna flow, but it will little zaps.
Air.
Yeah, it just zaps and kind of peters out. So yeah. All right, so then we had Ewald Jürgen von Kleist. Ewald, because it's Swedish. Jürgen von Kleist in 1700 to 1748 was when he lived, and he invented our Leyden jar in 1745 to store electricity. So the Leyden jar contained water or mercury and was placed on a metal surface with a ground connection. This is the first device that we ever had that could actually store electricity. So we could generate it with a static electricity generator, but we couldn't store it. So it was useful just to experiment with, but we weren't getting a ton out of it. Now we have a Leyden jar, so we can actually store a little bit. It's kind of like, sort of like a precursor to a battery. All right, and then in 1748, the Leyden jar was independently invented by a physicist, Pieter von, I'm going to get this one wrong, Muchenbroek, I think is who it is, 1692 to 1761, and or his lawyer friend, Andreas Caneus, in Leyden in the Netherlands. Okay, so you had von Kleist, Muchenbroek, and Caneus all working at the same time, trying to invent something to store electricity. And they basically invented the same thing at the same time. So they invented the same thing at the same time.
Not at the same time.
But the name, the credit for the name, kind of ended up going to Pieter von Muchenbroek and his lawyer friend, because they were in a town called Leyden in the Netherlands, and they've named these Leyden jars. So that's where the credit to the name goes. But they were independently working on these things. So Leyden jars could be joined together to store large charges. And this is interesting. So you don't just have like the one little jar, you can hook them all together. And when you do that, you can store a much larger amount of charge. So again, it's like a precursor to a battery. It's like the difference between having like a watch battery and a car battery, right? Very different. So we're getting somewhere. So then we have this famous experiment. In 1752, Benjamin Franklin, who lived from 1706 to 1790, demonstrated that lightning was electricity in his famous kite experiment. So you remember this, right? He sent the kite up on a little wire, tied a little key to it, lightning struck it, came down. Yes, the famous Benjamin. So there's a word for people like Benjamin Franklin. It's a word we use this, we talk about this word a lot in this class because we come across a lot of these guys. But Franklin was like, he knew a lot about science. He knew a lot about law. He knew a fair amount about religion. He knew a lot about writing. He was a diplomat.
It's an oddballs episode all about Franklin.
Franklin is a fascinating guy. And do you know, did you learn anything interesting about him in that episode? So here's the thing about Franklin. You like to think of these founding father types as these very like proper upstanding men with their white wigs, and they spoke proper grammar, and they were very classy people, right? Like that's the image we get. Benjamin Franklin loved fart jokes. He told inappropriate 12-year-old boy humor jokes all the time. Like he loved stuff like that. He was like a total nerd for 12-year-old boy humor. Like he really was. Like fart jokes were one of his favorite things, which is funny. You don't think of the founding fathers as somebody who tell fart jokes, but he loved them. So he was an interesting dude. So people like him though, people who know a lot about a lot. So Franklin Jefferson's another good example. If we're talking just founding fathers, Franklin, Jefferson, Hamilton, guys that know a lot about a lot of things are called polymaths. So you may come across other polymaths as you learn about people in history. Leonardo da Vinci is an excellent polymath. Yes, he knew a lot about a lot. There are people that learn a lot of diverse things at a deep level. So they have a very broad knowledge about a whole lot of like dichotomous diverse topics. Yeah. Yeah, exactly. Or then you got like religion over here and writing over here and science over here, disparate topics. All right, so then we have this guy. And this is the guy. This is the dude to remember when it comes to fun stories in science history. History is not boring. He's the frog guy. Yeah. So 1780, Italian physicist, physician and physicist. So he was a doctor too. He was actually an anatomist. So he studied anatomy a lot, right? Luigi Aloisio Galvani discovered that muscle and nerve cells produce electricity. Whilst dissecting a frog on a table, which isn't weird because he was an anatomist, dissecting a frog on a table where he'd been conducting experiments with static electricity, Galvani touched the exposed sciatic nerve, which is a nerve that in you runs from the back base of your spine down your leg. Okay. He touched the nerve in the frog, the sciatic nerve, and it caused its leg to jump. It's because the scalpel he used had a little static electricity in it. It had been charged. And he touched it to the nerve and the nerve jumped. So here's the crazy thing. When we talk about biology and chemistry, and even when we start talking about geology and all of these different types of science, in the end, if you whittle it down to the tiniest detail, it's all electricity. Biology is all electricity. Chemistry is all electricity. Think about it. Why are atoms bound together? Because there's a difference in electric charge between the protons and the electrons. Everything comes down to electricity. Electricity is like the most basic force, and it's everything. Rocks hold together because of the bonds, with chemical bonds within them, and those chemical bonds hold together because of electricity. Our brains are electrical, our hearts are electrical, our muscles are electrical, everything's electricity. So if you find electricity interesting, you'll find it everywhere. It's absolutely everywhere. So this is where we get into one of our greatest smackdowns in scientific history. So we talked about him in physical science. We're going to talk about him again because it relates here. No, we also talked about Edison and Tesla. Edison and Tesla had a huge feud. Well, here comes what this is a scientific wackadoodle story in history, but it's fascinating. So then you had this guy, okay? So we had Luigi Galvani, right? Frog moved. Now we have Count Alessandro Giuseppe Antonio Anastasio Volta. He had a short name to learn when he was a child. Hey, you want to learn to write your name? All right. Count Alessandro Giuseppe Antonio Anastasio Volta. I am grateful my mother gave me the middle name Nicole and not all of that, because that's a lot, right? So he developed the first electric cell, which is called a voltaic pile. You see volta, that's where we get the word volt from. When we talk about electrical volts, comes from volta. Okay, so a voltaic pile consists of alternating layers of two dissimilar metals separated by pieces of cardboard soaked in sodium chloride solution or sulfuric acid. So basically, you're creating a sort of like a battery is what he's doing. All right. So he determined that the best combination of metals was zinc and silver. So we'd alternate zinc and silver. And in between them, he had a solution of sodium chloride or sulfuric acid. What do we know about acids in solution? What is one of the characteristics of acid in solutions that would relate to this? They're good conductors of electricity, right? And what is sodium chloride in water? What is happening there?
Sodium chloride, there's ions.
Yes, so they're both, it's an electrolytic solution, right? So these are two conductive solutions he's using, all right? And this is what his voltaic pile looked like. All right, this right here is one of his actual voltaic piles, and it's in the Smithsonian Institute. This is an original one from the 1700s, well, 1800 when he developed it. So this is from 1800. You can actually go see it. It's in the Smithsonian. That's where it is. So it's alternating discs of silver and zinc, and in between them are cardboard discs that are soaked with electrolyte or something that will conduct electricity. So we're going to come back to Volta and Galvani in a minute. But as we move forward, now in 1800, we get this English chemist, William Nicholson. and a surgeon named Anthony Carlisle, and they separated water into hydrogen and oxygen using electrolysis, which is what you are going to do today in lab. So the first time this experiment was done and like noted for the sake of history was in 1800, and you're going to be doing the exact same thing today in lab. So that's really cool. So you're going to be doing an experiment that people have been doing for 225 years. Pretty neat, right? It's an old one, but it's really cool. Then we have Johann Wilhelm Ritter, and he repeated Nicholson's separation of water into hydrogen and oxygen, and soon thereafter discovered the process of electroplating. So he observed that the amount of metal deposited and the amount of oxygen produced during an electrolytic process depends on the distance between the electrodes. Electroplating is, sometimes you'll get something that is like, it's silver plated or it's gold plated jewelry or silverware. And it's like, maybe there's steel, or maybe it's a spoon, maybe it's a silver plated spoon. So there's steel or some other metal. And then you put it in an electrolyte bath with electrodes, and then you put some chemical in that contains silver, and the silver will come out of solution and stick to the metal object that you're trying to cover. So you coat it in a very thin layer. That's electroplating. So he's the one who invented electroplating, Johann Wilhelm Ritter. And then we had Humphrey Davy. Humphrey Davy comes up every so often in science lessons. This guy did a lot of stuff. But he utilized the voltaic pile that Alessandro Volta invented, right, in 1807, so 7 years after it was invented, to isolate elemental potassium by electrolysis. And then he was able to pull sodium, barium, calcium, strontium, and magnesium out of compounds and isolate them. So he's doing this using electricity. So this is new. This is new. We're getting somewhere. Then we had Faraday. Faraday is one of the coolest scientists in all of history. This guy was big time awesome. He did a lot with electricity. So he began his career in 1813 as Humphrey Davy's assistant. And then he developed two of the laws of electrochemistry. The first law says the amount of a substance deposited on each electrode of an electrolytic cell is directly proportional to the amount of electricity passing through the cell. And he also said the quantities of different elements deposited by a given amount of electricity are in the ratio of their chemical equivalent weights. Faraday is so well respected historically that he's on British money. You know how we have like, who's on our money? George Washington's on the $1 bill. Lincoln's on the $5 bill. Who's on a $100 bill? Benjamin Franklin, the dude with the kite, right? Okay, so we have people on our money too, right? Faraday's on British money. He's on the 20 pound note. Now they use euros and stuff over there a lot too, so maybe we don't see his face as much. But he is a really, 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 really cool guy. So if you want to get into somebody who is a fun biography, Faraday.
So that's Faraday right there?
That's Michael Faraday. Yep. All right, so then Faraday also defined a number of terms. So here's one. The what is therefore that surface at which the electric current, according to our present expression, enters. It is the negative extremity of the decomposing body, is where oxygen, chlorine, acids are evolved, and is against or opposite the positive electrode. What have you got?
Electrode.
Which one? Do we know?
Electrolytic.
So it's going to be anode, which is an electrode. So you have two electrodes. You have anodes and cathodes, right? Now, do you remember, anybody remember anions and cations?
Yep.
Cations are positively adorable, right? And anions are angry onions. But look here, your anode is the negative extremity of the decomposing body. It is where oxygen is evolved. So today in your lab, where is your oxygen going to come from? Your anode or your cathode?
It's gonna come from the cathode.
From the anode, right? It's where oxygen is evolved. Yep. And it is against or opposite the positive electrode. All right. Now, what is the opposite of the anode then? What's the other electrode? That's your cathode. Very good. So your cathode is a surface where the current leaves the decomposing body. And it is the positive extremity. The combustible bodies, metals, alkalis, bases are evolved here, and it is in contact with the negative electrode. Excuse me, sorry. Ugh, I hate allergies. Many bodies are decomposed directly by the electric current, their elements being set free. And I propose to call these, you know?
Oh, electrolytic cells.
Electrolytes. Yeah, you're almost there. Yeah, electrolytes. So electrolytes are what he called the things that were leaving in and out. Your charged particles, right, are your electrolytes. So electrolytes, we can give Faraday credit for that word. Finally, I require a term to express those bodies which can pass to the electrodes, not from, okay? Or as they are usually called, the poles. Electrodes are called poles, right? Substances are frequently spoken of as being electronegative or electropositive, according as they go under the supposed influence of a direct attraction to the positive or negative pole. I propose to distinguish such bodies by calling those what? Which go to the anode. Eunice?
Positive.
What is those? Anions go to the anode, right? And then what goes to the cathode? Cations go to the cathode. And when I have occasion to speak of these together, what do you call anions and cations together? You know? Electrolytes?
Neutral.
Well, if you're talking about anions and cations in a sentence, I have anions and cations. I have ions, right? They're types of ions. So together they're ions. So this is Faraday. This is all Faraday. This is stuff we use every day in our day-to-day lives. Thank you, Faraday. The chlorine of the lead is an electrolyte, he says, and it is because it's chloride, right? And when electrolyzed evolves, the two ions, chlorine and lead, the former being an anion, the later being a cation. So yay, Faraday. Then we had John Frederick Daniel, professor of chemistry at King's College, London, which, by the way, has one of the best church choirs in the world. Just going to say. Actually, Cambridge, more so than London. So his research into development of constant current cells took place at the same time as Faraday. And the commercial telegraph system, at the same time as that commercial telegraph systems began to appear. So after Faraday, sorry. And Daniel's copper battery, 1836, became the standard for British and American telegraph systems. Now, you know we have a telegraph in this house, right? That runs from the pub to over here at this little table. And it is a functional telegraph. You can send telegraphs through it if you so choose. But you have to know how to understand and send Morse code, which nobody in this house has mastered yet, but we've played with it. So in 1839, Daniel experimented on fusion of metals with a 70-cell battery. He produced an electric arc so rich in ultraviolet rays that it resulted in an instant artificial sunburn. He gave himself a sunburn, y'all, in lab. These experiments caused serious injury to Daniel's eyes, as well as the eyes of the spectators. This is why when you're welding, you wear welding goggles, right? Like it's very bright. It can damage your eyes. So he evolved this electric arc, which is like, if you've ever seen, you ever seen power lines sparking or whatever, that's called arcing. So he evolved an arc that was so strong and so rich in UV that it damaged his eyes and gave him a sunburn. Dude. And some of the spectators. Oh, it probably permanent damage to his eyes. Sunburn lasts as long as a sunburn. So ultimately, Daniel showed that the ion of the metal, rather than its oxide, carries an electric charge when a salt solution is electrolyzed. So there's an early cell, and then these are ones used a little later. So now we get to this guy, 1864 to 1941. Walter Herman Nernst. Anybody know what year your grandparents were born? Most of you guys probably have.
My grandma was like 19. My grandpa was born in 1954.
I was gonna say, probably the fifties for yours,
My grandpa was born in 1943.
There you go. Okay, so this is perspective. So like my parents were born in 42 and 46. So this guy lived right up until the time that most of y'all's grandparents were about to be born or were born. So now we're getting very contemporary, right? All right. So Nernst's early studies in electrochemistry were inspired by Arrhenius' dissociation theory of ions in solution. Remember, Arrhenius said that if it's got a H plus, it's an acid, and if it has an OH negative, it's a base. Do you remember that? So he started studying electrochemistry, thinking about it, Arrhenius theory. That's how he was using it. Ions in solution. In 1889, he elucidated the theory of galvanic cell. Elucidated means to speak it out, to articulate it in a clear way, right? Of galvanic cells by assuming that electrolytic pressure of dissolution, which forces ions from electrodes into solution, and which was opposed to the osmotic pressure of dissolved ions. So he's getting really into this stuff. This is deep stuff. In 1889, he showed that how the characteristics of current produced could be used to calculate the free energy in the chemical reaction producing the current. And this equation, which we call the Nernst equation, relates to the voltage of a cell and its properties. And then independently of Thomson, he explained why compounds ionize easily in water. You remember Thomson with the plum pudding model?
J.L.T. Thompson.
Yes, the chocolate chip cookie plum, the same guy. That's who we're talking about. So he explained why compounds ionize in water. And this explanation, called Nernst-Thomson rule, holds that it is difficult for charged ions to attract each other through insulating water molecules, so they dissociate. So this explains why, if you put something like salt into water, why it dissolves, why it dissociates into ions. So terminology. Anybody know what, that's Michael Faraday, by the way. Anybody know what voltage is? A definition for voltage.
It's like when, so voltage is like, so a current is the flow.
Yeah.
The voltage, is like the resistance is the pressure, and
Yeah, there you said
voltage
it.
is how hard.
It's like it's like the pressure. What'd you want to say, Annabelle?
It's like how hard you push it.
Yes.
Voltage is the potential difference between two.
Yes.
Also the amount of energy that drives a reaction.
Yes. So it's the potential difference between two half cells, also the amount of energy that drives the reaction. It's like pressure. Yeah, it's the intensive property. The amount of voltage does matter. How about current? What's current?
Flow of energy in a,
Yeah, it's the flow. Yeah. So your current is the flow of electric charges in units of electrons per second. And it is an extensive property. Amount of current does matter. So high voltage does not mean high current necessarily. A primary battery is a non-rechargeable battery. So this is like a AA, AAA, C, D. Well, those you can recharge. You can charge your battery
those double
in a Tesla, like not the 12-volt batteries that are in most cars. No, those are primary batteries. But if you have like an electric car, those are rechargeable. Yes. Uh-huh. Yeah. You know what? AA, AAA battery, a 9-volt. You're going to use a 9-volt today in class. Those are primary batteries. Then you have secondary batteries, and these are rechargeable. Lithium. These are your cell phone batteries, your Tesla batteries, anything that you can plug in and charge, like your phone, right? Or your laptop. A what? Yeah, well, a normal car battery would be primary. They no, that's not true. They're secondary. They get charged by the alternator when the car drives. Yeah. So a tertiary battery, these are fuel cells, and they're not always considered batteries, though they have a constant flow of reactants. All right, so galvanic cells. A galvanic cell or a voltaic cell. So these induce a spontaneous redox reaction, that's what we did in lab last week, to create a flow of electrical charges or electricity. Non-rechargeable batteries or primary batteries, right, are galvanic cells. Electrons flow from the what to the what? From the anode, which is negative, since electrons are built up there, to the cathode. So here's the thing to remember. If electrons are flowing from the anode is the negative part of the battery. It's where the negative stuff comes out, not what the negative stuff is attracted to. What is the negative attracted to? The cathode, right? So it flows from the anode to the cathode. A galvanic cell produces an electrical charge from the flow of electrons. Electrons move due to redox reaction. Many examples of galvanic cells are power sources that generate electrical energy from chemical energy. Galvanic cells are quite common. AA, AAA, DC, etc. are all galvanic. Any non-rechargeable battery that does not depend on an outside electrical source is a galvanic cell. These are chemical cells. Conventional batteries supply electrical energy from the chemical reactants stored within them, and these reactants are consumed. Then the battery is dead, right? You've all had a dead battery experience before, right? The alternative approach would be to feed the reactants into the cell as they're required so as to permit the cell to operate continuously. In this case, reactants can be thought of as fuel to drive the cell, hence the term fuel cell. So fuel cells differ from batteries in their oxidizing and reducing agents are gases introduced from the outside. So this is just more about fuel cells. We don't need to go over it because you're not going to need it. So galvanic corrosion. You ever seen a battery do this?
Oh.
Yeah. This is electrochemical process in which one metal corrodes preferentially. So one's going to be more likely to corrode than another. And it is with electrical contact with another in the presence of the electrolyte. So here's the galvanic cells. And here's this little thing that helps you remember. Your current is what's flowing through this little tunnel. Your amp is like kind of the size of it. The volt is how it's being pressed. And the ohms is your resistance. So we use this sometimes when we're trying to remember the different, ohm. So electrolytic cells require an outside electrical source to initiate redox reaction. The process of how electric energy drives non-spontaneous reaction is called electrolysis, and that's what we're doing in lab today. Whereas galvanic cell uses a redox reaction to make electrons flow, the electrolytic cell uses electron movement to cause the redox reaction. So an electrolytic cell is one kind of a battery that requires an outside electrical source. And the reaction is not spontaneous. So this is about Gibbs free energy, which you don't really need to know so much, but it's there for you, so you have access to it. Electrical energy is used to power an electrolytic cell. The most common form of electrolytic cell is the rechargeable battery, like in your cell phones, right? While the battery is being used in the device, it acts like a galvanic cell. It acts like a AA or AAA or whatever. But when the charge gets low, you can plug it in and bring in more power from outside where it can be stored and then released in your redox reaction, right? So electrolysis, which is what we're doing in lab today. Electrolysis is a process by which electrons are forced through a chemical cell, thus causing a chemical reaction. The positive charge usually attracts electrons. The electrode providing electrons is called the cathode because the reduction takes place on it. Electrolytic cells. Electroplating is the process of plating one metal onto another by hydrolysis. So we talked about this, electroplating. Here's how electroplating works. If it will play, maybe. Ah,
It's not sharpened this pencil.
hold on. It's fine.
This can be decorative, as in silver plating, or practical. With industrial parts, for instance, zinc or cadmium plating prevents the underlying metal from rusting, while nickel or chrome plating protects against wear. You can plate almost any type of metal. Let's follow some steel aerospace parts as they're about to be plated with cadmium to make them corrosion resistant. For the plating metal to bond properly, the steel surface must be free of contaminants such as oil and grease. Workers suspend the parts over a vat of boiling chemical solvents. As the hot vapor comes into contact with the colder metal, it condenses, dripping down into the vat and taking any contaminants along with it. The remaining solvent residues evaporate, leaving the parts squeaky clean and dry. Next, a worker wearing protective clothing sandblasts the parts with aluminum oxide powder, a strong abrasive. This roughens up the surface so that the plating metal will adhere better. The most common plating metals for industrial purposes are zinc, chrome, and nickel. Think motorcycle parts or sink faucets. Decorative items, on the other hand, are more likely to be plated in tin, brass, gold, or silver.
There's a
Traditional
dog.
tea
Okay,
sets,
it's just
for
not boxed
instance, are
up.
often made of silver-plated copper or zinc.
Or maybe not, maybe he brought it down.
The plating process is called electroplating because the key to it all is electricity.
Okay,
They
let me
start
figure out who that
by
is. I don't know who that is. Hold on. Don, do we know? Mojo. Mojo. Hey, Mojo, Mojo, outside. Come in, come here. Mojo. One second. Yeah, that's Mojo. Yeah. Mom, do not let Otto out. Mojo's in the backyard. Just walk to the house. Yeah. Y'all sit back down. Then I'll call my neighbor so she can come get him.
strands of copper wire to a copper support frame. Copper being the best metal for conducting electricity. Then they attach the steel parts they'll be plating. When they hook up this support to an electric current, electricity will run from the support through these wires right to the pieces. They do the electroplating in a tank. After filling it with water, they add a handful of chemicals to help conduct electricity, because water alone won't conduct it sufficiently. Along the sides of the tank, in bags, are metal baskets. They contain bars or balls of the plating metal, in this case cadmium. Workers connect the support frame with the steel parts to the negative terminal of an electric source, the baskets of cadmium to the positive terminal. And then they switch on a steady DC current, no stronger than 6 volts. The electricity dissolves the cadmium, lacing the particles with a positive charge. They travel through the water and attach themselves to the negative charged steel parts, creating a smooth and even layer of cadmium. Thin plating.
He's a sweet dog.
requires
He's
minutes
just
in the
huge.
tank, plating several hours. Then workers rinse the parts in water.
Oh, no, he's a big
for
baby.
minute To remove the chemical residues. To make the parts even more rust
Yes.
resistant, workers immerse them in a series of compounds. This triggers. a
Okay,
chemical
okay,
reaction in the plating
sorry.
in-
We're having a little, Mojo just strolled right in the front door behind everybody. So I put him in the backyard, but I can't take him home because I'm teaching. Can you get a leash? Take him back, take him home. Yeah. like this. He's huge. Okay, so nothing like that. Just walking back. I'll help you. Hold on, I'm sorry, gang. Here. Come. Sorry, he's a giant baby, but he's huge. Yeah. He's never walked in my house before. That's funny. And I tried texting. Oh God, Brett is getting his leash and is on his way. He'll meet Drew. Probably halfway. That's so funny. He just walked right in the house. All right, so yeah, that's funny. All right, so so for your homework, you're going to be asked to look for the following things, right? Try and find some information on your galvanic cells, electrolytic cells. Yeah, and then these are going to be your topics. Oops, sorry. But I wanted to real quick in the other groups, in the other class thing, I wanted to show you the Galvani story. And I got to do it really fast because we just got sidetracked. So hold on a minute, Annabelle. So this is our great smackdown. Here's our guy Galvani, right? Italian physician, biologist, philosopher, physicist, experimenting with his frog legs in a Leyden jar, remember? And then the leg jumped. So then what did he do? He got fascinated with something he called bioelectricity, which isn't even a thing. Electricity is just electricity, but he called it bioelectricity. So that's what his diagrams look like. That's fun, right? Nothing creepy about that. So it led him to place frog legs outside with wires running to them. And now historically, this took place right after Benjamin Franklin with the kite. All right, so we had to keep that in mind. Imagine him as your neighbor. So then things get really weird. So picture this. You're strolling past Galvani's home. This is actually Galvani's home. It still stands today, but without the cars in the modern street. So probably more like that, right? And anyway, you're strolling past and you notice his lovely home. And look, oh, this beautiful wrought iron fence that goes around it beneath stormy skies. And you see this, a bunch of frog legs dangling from a fence, because this is what this dude did, right? Yeah. And this was real life. You were just walking by, and for real life, this is what you would see. Strolling by, minding your own business, right? So then what happened is he discovered this, he called this animal electricity or bioelectricity. And he thought it was a charged fluid generated by the frog that existed in some state of disequilibrium. And he thought that he had, in a way, reanimated a corpse, not so much. But he actually discovered the frog's nervous system could transport electric charges, which we know yours does too, right? So he knew that metals transmitted this mysterious substance called electricity, but came to the obvious conclusion that some kind of electricity or animal electricity was generated in the frog. That's not really what's happening, but he thinks that's what's happening. So he distinguished this kind of electricity from what he called artificial electricity, which was static electricity. He was calling that artificial, and he was causing this natural, but really they're the same electricity. So this was a landmark discovery. It changed the way physicians and scientists thought about the nervous system. So then he had this nephew, this guy, Aldini. Okay, and Aldini was a showman, very much a showman. And he started traveling all over Europe, and he was, quote unquote, reanimating corpses of dead animals. And yeah, humans. So here's what happened. It's known as galvanizing, but rather than dragging around a Leyden jar, he traveled with a voltaic pile, a type of battery, right? And his most famous demonstration happened in London, in 1803. So a 26-year-old man named George Foster had been accused of murdering his wife and daughter by drowning them in the Thames River. And he was hanged that day in London. All right. and his body was immediately transported to the Royal College of Surgeons, where before an audience, Aldini ran electrodes from his voltaic pile and detached them to Foster's corpse in various locations. Attaching electrodes to the jaw and the ear created a one-sided grimace. He even caused an eye to open, and the crowd was in awe. And now Aldini's aim was to learn more about how to save a person who experienced trauma and how to restart a heart. He thought this was a good idea. And that's the genesis of our modern defibrillators, right? Our AEDs. But here's what he ended up doing. He was just really fiddling around. He really didn't know what he was doing. He was playing around, sticking electrodes in different places. So he kept fiddling around with this guy's newly dead corpse. Remember, they hanged him because they thought he murdered his wife and his daughter. And so he moved an electrode to the bottom of this Foster's spine, and he sat up. The body sat up. Yeah. 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 And he sat up. And people freaked out. So does that remind you, do you know a story where a scientist reanimates a human corpse? Do you know a story about that? Classical horror story. What do you think, Annabelle? Oh, now do you suppose Mary Shelley, who wrote Frankenstein, was inspired by this, or was this inspired by Mary Shelley? What do you think? Who came first? So Mary Shelley got the idea from this experiment. That's where her idea for Frankenstein came from. Now, here's the crazy thing. He wasn't universally celebrated. His nemesis was Volta. Volta didn't like him. Volta said he had it all wrong. They had a feud that went on for years. But the crazy thing is, that term galvanize was Volta created the term, but he did it with an eye roll. Oh yeah, he's galvanizing bodies. But then it became like the thing that Aldini owned. Like, oh yeah, galvanize, it's cool. But Volta didn't mean it as cool. He was doing it in a teasing way. So the crazy thing is that device that Galvani's nephew Aldini dragged around with him to reanimate corpses was a voltaic pile. And who invented the voltaic pile? Volta. Whap, whap, whap. Thanks, Alessandro. That's not really the way he wanted that to go down. All right. You guys are good. So let's get lab out and come on in, gang.
Did I get my points on?
If you want. Hello, people. Colin, you're right there for you on the table is your, yep,